The force on a current carrying wire placed in some external magnetic field is often expressed with this formula, F equals IL cross B, Filb, right there. So I want to look at where this formula comes from and pay special attention to the fact that although this is often referred to as the magnetic force on a current carrying wire, it's actually an electric force on all the positive ions, the copper ions, if it's a copper wire, due to the net magnetic force on the free electrons that are moving through the wire. Right? That may sound more complex. It may sound like I'm making it more complex than necessary, but I hope you'll see by the end the important distinction I'm making here, or the importance of the distinction I'm making here between electric forces and magnetic forces. Okay, here's our wire once again, placed into some external magnetic field coming out of the page, and there's a current moving in this direction through our wire. Let's look at some of the charge, some of the free electrons drifting downwards in this wire. Let's say if we take a sort of cohort of charge occupying this particular cross section of wire, this sort of coin-shaped slice of the wire, if we're imagining a wire with a circular diameter and we're looking down on it. Let's say all the free electrons in that wire. So this contains a total charge dq. We'll make it a thin slice, so it'll have a thickness to it here, dl. And suppose they're all drifting downwards together with the drift velocity, vd. Okay, so this sort of collection of charge is drifting down. Now, according to what we know about magnetic forces, these charges will feel a magnetic force. Let's see, V cross B. So V is down, B field is up, so that points to the left, but they will be negative charges, so that flips it. We'll have a magnetic force on this collection of charge to the right. I'll just put the arrow here. There will be a magnetic force, FB, pulling on all this charge to the right as it drifts downward. Okay, let's get an expression for that. Let's see. Oh, if this is a very small amount of charge in total, an infinitesimal amount of charge occupying this infinitesimal little width of wire, then this will be just an infinitesimal force on it, dFB. Small amount of force on that little amount of charge. So we have that infinitesimal magnetic force on that charge equals dq times our drift velocity there, crossed with our magnetic field. Okay, we've seen previously that this quantity here, this combination dq times v, that can be expressed as the current I times dl. So let's rewrite this as I dl cross b. Okay, there's a sign change that would have to take place there. Let's see, if our drift velocity points downward, then our current is pointing upwards. I guess this, let's see, this dl should point in the same direction as our drift velocity, except these dq's are negative. Oh, Ben Franklin, what have you done to us? Okay, I guess, let's see here, what do I have to do to fix this? I suppose I think we'll have to put in a minus sign out front here. No, let's just do this. Let's make this dl vector point that direction. There, that'll do. That'll dl vector will point upwards like that. So dl crossed with b points to the right, as we had a moment ago. Okay, that does it. So dl is now in the direction of the current, and we're still getting this magnetic force on this collection of charge to the right. Okay, that's fine. It's just that VD and DL are not in the same direction now. I guess we'd have to have like VD, DQ VD equals the opposite of I DL. Well, in any case, I'm going to press onward here. This is the magnetic force on this collection of charge in this little slice of wire. I would like to find the total magnetic force on all such slices of wire. So let's find the total magnetic force on all the free charge in that wire, which we'll get by adding up all those infinitesimal little FBs. So that'll be I times the integral of dl cross b. I'm pulling I out because I, of course, is constant for all those little cross sections. Okay, B is also constant for all little cross sections, so this can be rewritten as I times the integral of all those dl's, and we'll kind of pull the cross B out off to the side over here. So adding up all those dl's, what we're going to get is the total length of wire, however long the section of wire is that we're adding up all of these little bits of dq for, and all those dl's will point in that direction. So I am going to call this vector capital L cross B, where the magnitude of capital L will be equal to the total length of our wire. Let's call that length, that total length there, L, and our vector L will point in the direction of the current. It's the sum of all those little dl's, and has magnitude equal to the total length of the wire. That's what we're getting here when we add up all the dl's. They'll all point that direction. So here is our magnetic force on our electrons equal to I times L cross B, or Filb. Okay, so now here the argument gets a bit more interesting. We should think of our whole wire as the superposition of this background of copper ions, these positively charged copper ions that are present, and on top of them, this collection, this sort of cloud of freely moving free electrons. The total charge of the system is 0, but we've got these positive charges which are not moving in the background of these negative charges which are moving with their drift velocity downward. So if this is the total magnetic force on all of those electrons, I want to do kind of a free body diagram down here for the entire collection of all the free electrons in the wire. They're all feeling this magnetic force given by ILB up here, IL cross B. Let's note that L cross B, once again, let's check that the direction is right. L points in this direction, B is out of the page, so L cross B points to the right. That's the direction of our net magnetic force on all those free electrons, pushing them this direction. Okay, but once we're in an equilibrium state, this whole collection of free electrons is not just going to be leaving the wire and traveling off on its own. They're still bound to the wire. These free electrons, while free enough to sort of move from place to place within the wire, they're still overall bound to these background copper atoms. So as they pile up against the right-hand side over here, the copper atoms nearby are going to be pulling back on them, preventing these free electrons from actually leaving the wire. Also, as we saw in the Hall effect video, this collection of positive charge over here, that's our copper ions, which will be pulling back on all these free electrons that are trying to be pushed this way by the magnetic force. So these copper ions are pulling back on the electrons, and the nearby copper ions are preventing the electrons from just leaving the wire altogether. So there is an overall binding force, a collection of actually many different electric binding forces on the collection of free electrons. Fe binding. Electric binding forces exerted on the free electrons by the background copper ions, preventing the free electrons from just leaving altogether. So we have kind of an equilibrium here, where our free electrons are drifting downwards, magnetic field pulling them that way, but there's binding forces from the nearby copper atoms pulling them this way. Okay, but Newton's third law holds. So if there is a net electric binding force from the copper atoms, the copper ions, on the free electrons, then there is, correspondingly, on our copper ions here, an equal and opposite electric force binding those copper ions to their surrounding cloud of free electrons. And by Newton's third law, these are equal and opposite. So looking at this FBD for the free electrons, they're kind of in equilibrium here. These forces are balanced. But looking at our copper ions here, they are only feeling that net binding force to the electrons. They're not moving, so they're not feeling a magnetic force. So the copper ions here, which possess the great majority of all the mass in the wire, this is really the mass of the wire here, they're feeling a net force to the right. This whole copper wire, when you run a current through it this way, is going to get pulled to the right. And the size of that force happens to be equal to the magnitude of this magnetic force on our free electrons, IL cross B. It is, however, an electric force, not a magnetic force. It just happens to have the same size as this magnetic force. It's kind of like if these were two children holding hands here, and someone grabbed this child's hand and tugged this way. Well, this child getting tugged that way will pull on this child, so that child gets tugged that way as well. The only external force here is this one. That's the external force, that magnetic force acting on just this child, just the free electrons. This pair of internal forces here sort of equal and opposite. They cancel out. So the net force on the system is ultimately the size of this external force. Boy, that's a lot of words to try and argue the following. That although this external force here, being a magnetic force, does no work, as we've seen before, that does not do work. This is an electric force. And electric forces can do work. So this net electric force on our wire here happens to have the same magnitude and direction as the magnetic force on the free charges. So it's easily mistaken for a magnetic force, but with the key difference that it's actually in nature an electric force. So it can do work. And this wire will get pulled to the right when it runs this current in this way through this field. And it will speed up and it will gain kinetic energy. This electric force on a current carrying wire will push the wire around and do work and add energy to it and speed it up and slow it down. Let's look at some examples next.